So here we're asked to perform the integral of x cubed plus 3 all over x squared plus 3x plus 2. So looking at this, the first thing I kind of realize is that the bottom line here has a degree of 2. Okay, in other words, we've got an x squared term. So what we're going to need to do is partial fractions to get rid of that and go down to just having a degree of 1. And once we've got that, we know that we can evaluate the integral of 1 on x as just being equal to the natural log of x. Okay, so in order to do our partial fractions and split it up, the other thing we need to think about is what's on the top line. And we can see at the moment that the order or the degree of the top line is higher than the degree of the bottom line. So that tells us that the first step is going to be doing polynomial long division in order to get the degree of this top line down. And then once we've done that, we can jump in and do those partial fractions. So let's start off with the polynomial long division. Alright, so to set this up, what we know is that the top line goes inside here, and I'm going to split this up so it's like plus 3, and then the bottom line, that's what we're dividing by, so that goes out the front. Alright, so now what we need to look at is the biggest ordered terms on both sides. So this one is our biggest ordered term, x squared, and this one's our biggest term inside that symbol. So now what we need to think about is how many times x squared goes into x cubed. And I would say that is going to be x times, because x squared times x gives us x cubed. So next what we want to do is do x times all of this and take it away from the expression inside here. So x times x squared is going to be x cubed. X times 3x, that's 3x squared. And x times 2, that's going to be 2x. So I said I want to take this away. And now we just look down. So let me just move this across even further, because that's the constant term, and this is like an x term. Alright, so x cubed minus x cubed, that's going to leave us with 0. So I won't write anything here. We haven't got any x squared term on the top line, so it's basically 0 minus 3x squared, which is going to leave us with negative 3x squared. Again, we don't have an x term up here, so it's going to be 0 minus 2x, which leaves us with negative 2x. And then we have 3 minus, we have no constant here, so 3 minus 0 leaves us with 3. Alright, so now we just need to go through and repeat this process. So I'll get rid of our little highlighting here, because now what we need to do is look at the biggest degree term here and the biggest degree term down here, which is negative 3x squared. So we need to figure out how many times x squared goes into negative 3x squared, and I would say that would be negative 3 times. So now we just go through that process again, where we multiply the negative 3 by this expression out the front, and then take it away from what we've got here. So negative 3 times x squared is going to leave us with negative 3x squared. Negative 3 times 3x, that's going to leave us with negative 9. And then negative 3 times 2 is going to leave us with negative 6. So we need to take all of this away from what's above. So negative 3x squared, this is going to be plus 3x squared, is going to leave us with 0, so I won't write anything here. We've got negative 2x, this is going to turn into a plus 9x, so that's going to leave us with 7 overall. And then we've got 3 minus negative 6, so it's a plus again, so 3 plus 6 leaves us with 9. Alright, so now the order of this, alright, this is next to the 1, it's lower than what we are dividing by. So this is where we can kind of stop. So that means, if I write it over here, our expression of x cubed plus 3 over x squared plus 3x plus 2 is going to be equal to what we concluded up the top here. So x minus 3, plus we have this as a remainder. So we can write the remainder as 7x plus 9 divided by what we wanted to divide by anyway, which was the x squared plus 3x plus 2. And now we should be able to do partial fractions on this part because the degree of the top line is smaller than the degree of the bottom line. So that's going to be my next step. So partial fractions. So let's just take out this piece that needs the partial fractions performed on it. So we've got 7x plus 9 over x squared plus 3x plus 2. Now, to do partial fractions, it's going to be good for us to put this into two brackets rather than having it as a second order polynomial. So let's do that as a side step over here. So what we want is the front number times the back number. So 1 times 2 is 2. And we have 3 for the middle number. So we need two numbers that multiply to give 2, but add to give 3. And I think that's pretty easy. There's only one option. For the multiples of 2. 1 and 2, if you multiply them, gives 2, and adding them together gives 3. So x squared plus x plus 2x, alright, plus 2 is the same thing. All we've done is split that middle term. Factorising, I'm going to get x outside of x plus 1 when I factorise these two terms, and 2 outside of x plus 1 when I factorise the second two terms. And then if I bring the bracket part out the front, I get x plus 1, and I'm left with x plus 2. So that's the factorised version. So let's pop that in here. So we can write this as x plus 1, x plus 2. So now we just need to create our dummy fraction. So we can just split up the two brackets now. So I'm going to have some constant a over x plus 1 and some constant b over x plus 2. Alright, so the next step is to try and figure out a and b, and I can do that by first getting a common denominator across all of my terms. So if I multiply this first fraction here by x plus 2 over x plus 2, alright, I'm going to have the same denominator as what's over here. And then if I multiply this fraction by x plus 1 over x plus 1, alright, again I've got the same denominator now on the bottom line. And since I'm multiplying by, say, x plus 1 over x plus 1, that is going to cancel out with each other, so it's the same as multiplying by 1. So the equation hasn't changed. Alright, so now that I have a common denominator across all of these terms, it's going to cancel out. So we can drop all of this, and we're just left with 7x plus 9 and these two parts here. Alright, so now we can pick some convenient values of x in order to get a and b to fall out. So the first one, I'm going to let x equal to negative 2, because what's going to happen here is negative 2 plus 2 goes to 0, so that drops out, and all that you're left with is b in your equation. So it's going to be 7 times negative 2 plus 9 is equal to, well, we said this is going to drop out because negative 2 plus 2 goes to 0. So then we're just left with b of negative 2 plus 1. So this is going to be negative 14 plus 9, which is the same as negative 5. And negative 2 plus 1 goes to negative 1. So that means that b on its own is just going to be equal to 5. And let's do this once more with a different value of x. If I pick x is equal to negative 1, it's going to drop that bracket to be 0. So we're going to get 7 times negative 1 plus 9 is equal to a negative 1 plus 2, and again that drops to 0, so I won't bother writing it out. So on the left hand side here then we've got negative 7 plus 9, so that leaves us with 2, and we've got a times, this is going to be 1, so that means a is going to be equal to 2. Alright, so let's go back and write our fraction out then. So I might just add it on the end here. So a we've just said is equal to 2, and b is equal to 5. So now we have x on the bottom line for both of our fractions, which means that we should be able to go and apply the rule. So now that I have x on the bottom line of both of my fractions, what I should be able to do is apply the rule that we talked about at the beginning, where it's equal to 1 on x dx. You can integrate that for natural log of x. So that's really the last step, is to actually perform the integration. So if we scroll back down, what we want to integrate is our function, which we had up here was equal to x minus 3 plus the part we did partial fractions on. So I can write this as x minus 3 plus, and we rearranged what our partial fraction part looked like to be 2 on x plus 1 plus 5 over x plus 2. Alright, so all of that is equal to that initial equation that we were given. So now it's in this form, it's fairly easy to go ahead and actually integrate this. So this is just a polynomial one where we can add 1 to the power and divide by the new power. So x squared on 2. Same here, when we apply that rule, we're going to end up with just 3x. These ones, we're going to need to apply our log. So we can write this as being equal to 2. That's the constant that stays out the front, outside of the natural log of x plus 1, plus this one, the constant stays out the front, multiplied by the natural log of x plus 2. And because it's an indefinite integral, we're going to end up with the plus c. So this would be the answer for that integration. Now just as a quick side note, if you weren't sure how to jump straight from this to this, because it doesn't look exactly like 1 on x, you can use integration by substitution. So say we just take this fraction here as an example of that. So we want the integral of 5 over x plus 2 with respect to x. We can let u equal part of our equation, and I picked the more complicated part, so x plus 2. If we take the derivative with respect to x, this ends up just being 1, and I want to rearrange this for dx so they can substitute it in up here. So we're just going to get dx is equal to du when we do that. So we can rewrite this equation with the integral. 5 stays the same, and we let x plus 2 equal to u, and we can replace this with du. So now this kind of looks like that rule that we had where we just have directly 5 over u. So when we integrate that, it's going to be 5, our constant out the front, times the natural log of u, and of course it's indefinite, so we'd have our plus c. And then if we wanted to, we could substitute back in. We know u is equal to x plus 2. So this here is the same as what I had originally. So that's pretty much all there is for that video, and I'll see you in another one.